Hey there. In this video, we're going to take a look at the first lesson in our chapter 8, which is talking about how we can use integrals to illustrate net change. It's actually a topic that we've discussed earlier in the trimester, but let's get into it. The essential question is, what's the difference between displacement and distance, and how can I use integration to find them? Again, something that we've kind of scratched the surface on in the past. But to begin, using the substitution u equals root x, evaluate the integral of e to the root x over root x dx from 1 to 4. So if I use u, or if I let u equal the square root of x, then du should equal 1/2 times x to the negative 1/2, because square root of x is just x to the 1/2 power. Du should also have dx with that. And if you think about what du is equal to, another way to write this would be 1 over 2 square root of x dx. And I definitely don't see that du directly in my integral, but if I take the original problem and write it as e to the root x times 1 over root x dx, now I can see a similarity between what I have set as du and what I have in the integral. So I'm going to end up doing here is I'm going to take and multiply both of these by 2, and that would give me 2 du is equal to 1 over root x dx, which is a perfect match for what we have right there. So that portion is going to be multiplied by 2 du. And then e to the root x would become e to the u. And again, now you have a decision to make. Do you want to keep the bounds in terms of x from 1 to 4? Or we could switch the bounds into values in terms of u. So if I say u is equal to root 4, then my new upper bound would be 2. And if I say u is equal to root 1, then my new lower bound would still be 1. So I'm going to switch this from, instead of 1 to 4, going from 1 to 2. And now all I'm going to do is work on integrating and finding the value of that integral. I can remove the 2 as a common factor. So this is 1 to 2 e to the u du, which is very convenient because e to the u is its own antiderivative. So we should have 2 e to the u evaluated from not 4 but 2 down to 1. So this should be 2 times e squared minus e to the first. And this is why it's important to read directions, because we didn't even have to get all the way down to the answer. I got so excited to do calculus this morning that I didn't even look at the answer options. But clearly right here, 2 e to the u du, I see b and c both kind of look like that, but c has the correct switched bounds. So 2 times the integral from 1 to 2 of eu du. All right, so the answer was C. Went further than we had to. All right, okay. When we're talking about the difference between displacement and distance, remember, distance is like whether you're moving forwards or backwards, that is counting, that is increasing the value of distance. But if you walk 5 feet forward and 5 feet back, your displacement is the change in your position from beginning to end. So if I walk 5 feet forward, 5 feet backwards, the displacement is 0, but the distance traveled is still 10. So effectively, distance is just the absolute value of displacement within each set of movements. So again, moving forward counts as positive for both distance and displacement. Moving backwards counts as a negative for displacement, but it still counts as a positive value for distance traveled. So for instance, this beautiful graph of this honeybee, we see that the velocity is split into a bunch of different segments. So in the first 2 seconds, the B is traveling 200 feet forward from what I believe to be 3 to 5. The B travels 200 feet backwards, or 200 feet in the negative direction. And then from 6 to 8, 200 feet forwards, 9 to 10, 100 feet backwards. So the total distance traveled, I'm just going to take all of those values and add them up, add their individual absolute values up. So the total distance traveled would be 700 feet. But when it comes to displacement, I'm going to take the first 200 since it was positive, but then the next 200 was negative. So we're going to subtract 200, and then the next was positive, and then the last segment was moving backwards. And what we end up with is a grand total displacement of 100 feet. So that B traveled 700 feet total, but it ended up only 100 feet away from where it began. Okay, so just a quick reminder of displacement versus distance. On a velocity graph, again, this is not a word problem. There's no context, but if I ask you to find the displacement in the first 5 seconds, I see from 0 to 2, there's a distance traveled of 4. From 2 to 4, there's a distance traveled of 2, but it is negative, so I'm going to take it away. And then from 4 to 5, there's a positive displacement of 2 as well. So we end up with a displacement of 4 meters. Okay, but if I'm asking for just the total distance traveled, I'm going to take those 3 values, 4, 2, and 2. I'm going to add them all up, taking each individual absolute value, and we get a total of 8 meters for distance traveled. Find the final position of the particle if the position at time t equals 0 is 7 meters. So if I'm looking for the final position, that's basically asking, take the displacement in those first 5 seconds. And it's telling me that when t equals 0, so the position at time 0 is equal to 7. The total displacement over the first 5 seconds we already found is 4. So the final position, so the position at time 5 would equal 7 plus 4, or 11. 11 meters would be the final position after 5 seconds of this particle. Again, illustrating difference between displacement and distance traveled. When it comes to a position function, how could I find an expression for the position of this particle at time 4? Well, here's time 4. There's the particle's position at time 4. So I'm just going to say that is s of 4. It's not a velocity function. I can just plug in 4, and whatever I get out for the y-coordinate is my position at time 4. The position at time 0 would be something similar. I would do s of 0. I know that's equal to 4 because I can read that, but we'll just leave it s of 0. And the displacement of the particle during the first 4 seconds would be the position at 4 minus the starting position at 0, and that will tell me the total displacement. You can see down below the extension says, is the displacement of this particle the same as the distance it traveled? And the only time that's going to be true is if the particle is moving in a positive direction at all times. You can see from time 2 till time 4, there's a slight backwards movement. You can see that the slope of the position curve is negative, meaning that the velocity is negative. And so that slight negative velocity, or that slight negative movement, is going to automatically set the displacement and total distance traveled as different values. They will not be the same because that negative movement is counting as a negative for displacement, but it's counting as a positive for velocity, or sorry, for total distance traveled. So is the displacement of this particle the same as the total distance? No. The particle, this is one way you could say it. The particle is moving backwards, or negative, is moving backwards from t equals 2 to t equals 4. Okay. So again, that is if I'm given the position function. I'm not looking for the area under the curve. That is not what will tell me displacement or distance. Based on the position function, my current position is just the output of that function at a specific time. If I am given the velocity function, okay, so this is the velocity function for the previous graph, to find the displacement of the particle during the first 4 seconds. Okay, so if I want to find how far this thing is in total it has traveled in the first 4 seconds, or the difference between its position at the beginning and at the end, what we can do is we can simply find the integral, or the area under the curve, from 0 to 4 of the velocity function. Okay, and by finding the integral, that negative area that we see between the curve and the x-axis from 2 to 4, that will take into account the fact that that particle is moving backwards for that short period of time. And again, displacement, I want to include that negative value. If I am looking for the distance traveled, okay, there's 2 ways to do this. If this were a calculator question and you had access to a function or an equation for the function, we could do the integral from 0 to 4 of the absolute value of the velocity. Okay, so what that will do is that will effectively take and reflect that small piece of the curve back above the x-axis. Or if you do not have access to a calculator, or like this, if you are not given an equation for that curve, I'm going to integrate from 0 to 2, knowing that this is a positive value. But then the integral from 2 to 4 is going to end up yielding a negative number. So what I'm going to do is I'm going to subtract that second integral, or I'm going to subtract the value of the area between the curve and the x-axis from 2 to 4, because that negative area, when I subtract it, will effectively turn it into a sum of 2 areas. And if I'm looking for total distance traveled, this is going to be the preferred method. Again, you could just throw absolute value around the function if you knew the equation for that function. All right, moving on. So here's kind of where we get into the main point of the lesson. It says a particle moves along the x-axis at a position of 5 and then moves along the x-axis with a velocity of t squared minus 4. So it says for times between 0 and 10, when is the particle moving left, right, or stopped? So this is essentially a number line that we can create that we've done for the first derivative test in the past. Instead of putting arrows, I'm going to put my endpoints of 0 and 10. I can see that my velocity function can easily be factored into t plus 2 and t minus 2, which means that the velocity is going to equal 0 at t equals negative 2 and t equals positive 2. I'm not worried about negative time in this regard, so I'm going to go ahead and put 2 on here. And then if I plug in a value between 0 and 2 into the velocity function t squared minus 4, something like 1 squared minus 4 is going to be a negative value. So I'm going to have a negative velocity from 0 to 2, and then I would have a positive velocity from 2 all the way up to 10. So when is the particle moving left, right, or stopped? I'm going to take this and try to shrink it. Okay. I would say the particle is moving left from 0 to 2, and technically it is moving left when time is 0, so I can say 0 less than or equal to t less than 2. It is stopped when the time is equal to 2, and then it is moving to the right or has a positive velocity for the rest of the time, so 2 is less than t, which is less than or equal to 10. And then question 2, it's asking, okay, what is the position on the x-axis when t is 10? So tell me, where's the particle at? And what I'm going to do is I'm going to find the integral, I'm going to find the area under the curve from 0 to 10, which will give me the displacement in those 10 seconds. And then knowing that the particle starts at a position of 5, because that's a given value up here, the x-axis It starts at a position of 5. I'm just going to add 5 to that. So the position after 10 seconds is going to equal 5 plus the integral from 0 to 10 of t squared minus 4. And if I integrate that, I would have t cubed over 3 minus 2t, minus 4t, evaluated from 10 to 0. This is the displacement in those 10 seconds. So if I plug in 10, this is going to give me 5 plus 10,000, or 10 cubed is 1,000 over 4. That would be, why is it over 4? It should be over 3. So this is 1,000 over 3 minus 40. That is the position, or that is the particle's position at time 10. And then if I subtract 0, I know it's not actually at 0, but for the sake of the integral, I have to do 1,000 thirds minus 40, and then subtract 0. So this would end up being 5 plus 1,000 minus 120, because that's 40 thirds, which is 5 plus 880 over 3. If I wanted to keep it exact, I could change 5 into 15 thirds. 880 thirds. So the actual position on the x-axis for s of t, or s of 10, I guess, would be 895 thirds, or there's a decimal approximation certainly for that. Okay. But that is the position of the particle after 10 seconds. Okay, that does not tell me the total distance traveled. So in order to find the total distance traveled, I do not have to worry about the 5, the starting position of 5. What I would instead just do is I'm going to integrate from 0 to 2, but I know this is negative, right? Because I know that the velocity is negative between 0 and 2 seconds. So another way I could do this, instead of just applying a negative out front, is I could flip the bounds. So I could integrate as a lower bound of 2 and an upper bound of 0, essentially integrating backwards, which would turn that negative value positive. So I'm going to do that. I'm going to integrate from 2 to 0 of t cubed minus 4. And then I'm also going to integrate from 2 to 10. And that I am going to integrate 2 is my lower and 10 is my upper bound, because I know that velocity is positive. So t squared minus 4 dt. Okay. Either way, I have the same antiderivative. I'm going to integrate that from 0 down to 2. And then I'm also going to integrate the same thing, t cubed. Let's get this 2 out of here. I'm going to integrate t cubed over 3 minus 4t from 10 down to 2. Okay. Plugging in these values will get it's going to get a little annoying, but when I plug in 0, that's convenient. I just have 0 minus 0 in my two terms. And then I always am subtracting the lower bound. Remember, this should be a negative number. So 2 cubed over 3 would be 8 thirds minus 8. 8 is the same as 24 thirds. So in the first integral from 0 to 2, I end up with 0 minus negative 16 thirds. So this value would just end up being 16 thirds. That is the total distance traveled from 0 to 2. Okay, the velocity is actually negative, so it is moving backwards 16 thirds. But for the sake of total distance traveled, I need that positive number. And then if I add to that, we already did this calculation, but this is 1,000 thirds minus 40, which again I'm just going to put as 120 over 3, minus, and then I could plug in 2, but I already know what 2 is. I know 2 is 16 thirds over here. Okay. Because we integrated, we already plugged in a value of 2 and got 16 thirds in the first integral. And so what I end up with is 1,000 thirds minus 120 thirds. So that's back to my 880, but then I am subtracting another 16. I mean, those 16 thirds are going to end up canceling out, but what this would give me is... Oh, okay. So we got to be a little... they shouldn't cancel out. And the reason they shouldn't is if you look at that integral value, 8 thirds minus 24 thirds, that should be negative 16 thirds. And I did not call this negative 16 thirds, but I should have. So what ends up happening here is I have negative 16 thirds when I plug in 2. Let me just clean this up a little bit. So I'm subtracting negative 16 thirds, which will add 16 thirds back on. So here I've got 880 thirds plus 16 thirds. So 16 and 16 is 32, plus 880. 880 would be 912. So 912 over 3, which is actually just 404. So 404 is the total distance traveled, and that unit, we don't have a unit. Doesn't say meters or feet or anything like that. So we could just say 404 units is the total distance traveled. And again, the 404 comes from 912 divided by 3. That's not 404, that's 304. Putting myself out there, trying to do this math in my head. Already messed up 2 very simple calculations. But, so the position at time 10 is 895 over 3, which is, whatever, 298.3. But the actual distance traveled in those 10 seconds is 304 units. So that is kind of the main difference between position, asking about like final position, so asking about displacement, versus total distance traveled in a time frame. Okay. A lot of math going on there, but hopefully that kind of illustrates the difference. We'll do a couple more here real quick. Oil is moving through a repaired pipeline at a rate of 12 e to the t over 5 gallons per hour, where t is the total number of hours since the pipeline was repaired. It takes 24 hours for the pipeline to reach maximum capacity. So how quickly is oil moving through the pipeline immediately after its repair? So how quickly is oil, so it's asking for a velocity when time t is 0, or a rate when time t is 0. So the rate at time 0 would be 12 times e to the 0 over 5, which is just 12 times 1, because e to the 0 is 1. So we could say 12 gallons per hour. Okay. And then it says it takes 24 hours for the pipeline to reach maximum capacity. How quickly after it reaches maximum capacity? So it's basically asking what is R at 24. So 12 times e to the 24 over 5. Well, that's going to equal, I'm going to have to, there's no other real good way for that. I'm just going to have to go calculator on this one. I can get an approximation at least. So 12 e to the 24 fifths. And I can see that when the pipeline is full, is at its maximum capacity, it is flowing at a rate of 1,458.125 gallons per hour. Let's get this out of here. Gallons per hour. Okay, how many gallons of oil travel through the pipeline during the first day? First day it comes back online, so it's asking in those 24 hours. So we're just going to simply integrate from 0 to 24 of 12 e to the t over 5 dt. I'm going to go ahead and remove that 12 out of the integral. So I end up with 12, 0 to 24 of e to the t over 5 dt. I could do a quick little u substitution here. I could say u is t over 5, which then would make du 1/5 dt, or 5 du would equal just dt, which would mean my integral now becomes e to the u, but then instead of dt, I would replace that with 5 du. Right, so this is swapping out for that. And here I'm swapping out for just e to the u. You can see I left the bounds off because I do have to plug that in. So if u is 24 over 5, that I can just decimal approximate as 4.8. And then if u is 0 over 5, that is still 0. So my new bounds would be from 0 to 4.8. I'm going to go ahead and remove the 5 out of that integral as well. So my constant multiplier on the outside would be 60. So I'm going to integrate from 0 to 4.8 of e to the u du, which again is its own integral. So I have 60 times e to the u evaluated from 4.8 down to 0. And this ends up with 60 times e to the 4.8 minus e to the 0, which isn't 0, it's 1, so we need to have that in there. And then I'm just going to go ahead and plug that value into the calculator. So let's bring the calculator back, send it over here. I got 60 times e to the 4.8 minus 1. And I can see the total number of gallons over that first day as 7,230.625. So 7,230.625. 7,230.625. And that is a total number of gallons that have flown into the pipe over the first day. So you can see the rate in the beginning was 12 gallons an hour, which is pretty slow. Rate at the end is 1458 gallons per hour. That's quite a bit faster. And then if you integrate over the entire 24 hours, we end up with 7,230.625. Okay, last problem that we're going to take a look at is a store manager spends 1 minute each hour counting how many people come into a store and records it in the table below about how many customers visit his store during this 5-hour stretch. So during the first hour, you can see that he counted 0 customers per minute. And then during hour 1, there's 5 customers per minute, but we could bulk that up to 300 customers per hour because we're just going to multiply by 60. So really, I'm going to take all these values and multiply by 60. I got myself second guessing my own mental math. So there's 180, and then this is 0. And so one way you could do this is, right, we've learned the rectangle rule, the trapezoid rule. We have really any method that we could do to estimate. What we've seen in the past is that the trapezoid rule is going to be the most direct way to find an estimate for the total number of customers. So what I'm going to say is the trapezoid rule was 1/2 and then the width of each interval. So 1/2. So the area using trapezoid rule would be 1/2 times the base or the width of each time frame. In this case is 1 hour. So I'm going to multiply by 1. And then we're going to multiply by, the first trapezoid would have a left-hand base of 0 plus a right-hand base of 300. And if you remember, the trapezoid rule basically says every interior output value is used is used twice, once for the trapezoid immediately preceding it, and then once for the trapezoid immediately following. So I'm going to double 240 and 540 and 300. I'll also double 180, and then I'll use, I got to actually double that, 2 times 180, and then add 0 to that. And so what we end up with is 1/2 times the values 0 plus 600 plus 1080 plus 480 plus 360. What I also could have done is notice that that's a 1/2 and basically cut all of these 2's because essentially distributed that 1/2. But either way, I could say this is 1/2 times the quantity. Oh lordy. I didn't put the plus 0 in here, but I guess I should. Plus 0. If you add all those up, let's just double check. 600 plus 1080 plus 480 plus 360. So 2520 is the value in the 2520, which would be 1250, 1,260 customers is the estimated amount that manager saw. So again, a concept that we have talked about before, but now we are really formalizing the idea of displacement versus distance traveled. And in this case, we're going to build on it from here.